Many people ask, is it possible to one day win the fight against cancer? We think that the answer to that question is yes. But in order to win that battle, we will need to develop the most fundamental Turing machine, or in more profane words, a universal computer. Of course, there are many possible applications, especially in healthcare, where more or even the ultimate computer power would definitely be of good use. But nowhere would this machine lead to greater impact, if not to say a revolution, than in the treatment of one of the greatest curse of humanity, cancer. Nowadays, cancer is treated with a great variety of means, but probably every honest doctor on this planet would agree if we state that the perfect treatment wasn't found yet. All known options have often terrible side effects, do not guarantee lasting healing, and can mainly only be delivered via painful and partially even inhumane procedures. It therefore has to be concluded that the current situation is far from good or satisfying. Even in cases where the patient can be cured, the suffering and the side effects caused by the state-of-the-art measures are too often unbearable. And there are also so many poor cases where all known methods fail. A perfectly side-effect-free and painless treatment is seen in the so-called monoclonal antibodies. Here, however, we have to adapt a complex organic system, namely the monoclonal antibody, to a single and always very individual counterpart. In other words, not only every patient is unique, but also his or her cancer is. This renders the task of analyzing the cancer and patient genome and finding its perfect antibody solution a 10 to the power 24 faculty problem at least, and requires all computers in the world put together to work for many years only for one patient with only one cancer problem. Now, some of you may think that we are only talking about simple gene code optimization problems, where we only need to find the right fit for the antibody to the cancer. Unfortunately, however, this is not the whole picture. Nature, apparently, has a knack of also writing between the lines, and so the genetic code alone is not the whole task. The proteins coded by the genes is one thing. The correct environment, presence of agents, catalysts, and fields to synthesize and, what often is much more, to fold them into their only suitable biological form is quite another. The sheer number of structural possibilities to the same chemical composition and the complex nature of natural human tissue renders the task of finding and constructing optimum and truly satisfying solutions impossible by classical means. What we need is not only a better understanding of the materials, dynamic processes and interactions, but more computational power to allow for brute force calculation of multidimensional problems arising with this application. Within only a few years, Dr. Schwarzer has published a huge variety of works which have mathematical answers to many different questions. Within those, answers and opinions are not decided, made up or felt, they are calculated. His recent book, The Theory of Everything, gives the theoretical basics and most fundamental starting point. Richard Feynman once said that in order to calculate and understand a quantum object, one should build a quantum computer. Our reality, however, is a quantum gravity one, and thus, in order to completely understand it, we better build a quantum gravity computer. Understanding its fundamental theoretical principles and along the way opening its core features shall be our first starting point. So what would be the most fundamental starting point for the construction of the most fundamental and universal computer? As humans tend to put their own desires and preferences into the things they intend to create, we here explicitly want to stay as general as possible and therefore simply take an arbitrary ensemble of properties which want to exist in accordance with a minimum principle. This simply means that the ball rolls into the valley and would not like to be placed on the hilltop. The rest now is pure math, and the outcome, as surprising as it may be, are the Einstein field equations. Our field equations, however, act in an arbitrary number of dimensions and do not necessarily only describe space and time. Now, the attentive observer will probably argue that there has to be missing something. After all, everybody knows that the Einstein field equations are not compatible with the quantum theory, right? Well, but is this so, really? Admittedly, usually Einstein's field equations are thought to deal with things like moving planets, galaxies, collapsing stars, and, of course, black holes. So, there doesn't seem to be much space for quantum theory, which only shows itself with the very small things like molecules, atoms, and elementary particles. But still, we could try for some more or less unusual transformation which we perform on solutions to the Einstein equations. Let this be motivated by the bold assumption that others simply might have overseen something. So, in the first line of this slide, we have such an unusual transformation, and in the second line, we have evaluated the so-called Ricci scalar. There's no need to know the exact meaning of the Ricci scalar, as it totally suffices to memorize that it has something to do with the curvature of space-time, and that it is just the most important ingredient or starting point for the evaluation of the Einstein field equations in the first place. Closely observing our result and studying its intrinsic degrees of freedom suddenly gives us one of the most important quantum equations. It is called the Klein-Gordon equation, and it contains the better-known Schrödinger equation and the Dirac equation. As a mere byproduct, we obtain the result that mass and the classical potential is just curvature of space and time. So, the quantum theory already resided inside Einstein's general theory of relativity. It was only hidden somewhere in those field equations. Can it really be that simple? We definitely have to look for a bit more proof. Let's just start with the most simple solution in 4 dimensions, where we try to find a scalar field, which we assume to be a constant. Now, and here I must ask you not to scream, suddenly we obtain the Higgs field, the very field some even named the God field, and which gives all particles its mass. Ah, yes, and talking about the devil. What is mass anyway? Well, with a new approach we find an answer easily. Mass is the entanglement of 2 or more dimensions. Of course, there are also immediately many philosophical questions and quite some consequences too, like, what is the wave function then? What does collapse of the latter mean? What is the meaning of the geometrized quantum theory? With the Einstein field equations governing it all, what does the quantization of its solutions mean? How does the non-approximated procedure look like? But the only thing we want to concentrate on here is the question about the most fundamental computer machine there could be within this universe. As most of our consideration is already published and would take quite a long and, what is more, rather boring time to elaborate, we shall leave it to the interested spectator to check our evaluations and directly move on to the currently most promising way for the realization of the first quantum or even quantum gravity computer. Here we have the classical quantum dot deposition, the Australian silicon doping with phosphor on a variety of biocompatible solutions by the means of organic spin molecules. Here we only pick the quantum dot deposition where indium arsenide is being molecular beam deposited on gallium arsenide. The size difference between the indium and the gallium then leads to a strain-driven self-organization which bring about the desired quantum dot structures. Still, there is a long way to go before we could use these structures in properly working quantum computers, but at least there already is a start. But why all this fuss about quantum computer? What is so special here? Well, while the classical computer can only handle zeros and ones, which is to say, two different states, the quantum computer uses reals and does all possible states in just one circuit time. This gives it an immense calculation power in comparison with a classical machine, at least for a variety of tasks. But having now also a metric approach for the understanding of the inner working of such a bit, we do not only see how the computer does achieve this all-in-one-moment calculus, but we also realize that such machines could be even more powerful. In fact, one might come to the conclusion that the intrinsic power of a single Einstein quantum bit could be the one of a whole universe, and it even could be a universe of its own.
And here an important, recently motivated add-on information. Dr. Schwarzer informed about this amazing possibility to win the battle against cancer and many other diseases, including those caused by viruses, on an invited talk at the University of Florida in Orlando. This was in May 2019. One of the immediate questions after he had given his presentation was, and why would the pharma industry be interested in such a technology? After all, we need to make money, and this technology seems to solve almost all health problems where we currently have our most potent markets. Well, that every industry needs to make money is out of the question. But the tycoons should not be helped by the politicians to maximize their profits and stop competitive and often much better technologies to at least have their chance. Especially in the light of the current corona crisis, we invite everybody to draw his own conclusions.
Thank you for your attention. If you are interested in learning more about what SIOmec is doing, please feel free to watch our videos, which we have linked in the text below.